तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have been discussing the bipolar junction transistor. So far we have considered the basics of transistor action, and then we have seen how the transistor can be used as a small signal amplifier. In the previous lecture we estimated the alpha and beta of the transistor and we drew the energy band diagram. Then we have been discussing the various configurations of the circuit configurations in which the transistor operates, that is the common emitter in addition to the common base configuration. In the common emitter configuration we showed that you can get power gain, that is in addition to voltage gain you also get a current gain. Now towards the end of the lecture we were trying to develop from a single transistor and a power supply and a load resistor the complete circuit that we normally employ for a common emitter transistor. So let us look at this circuit that we had drawn in the previous lecture. We came to this circuit starting from here. This is the basic circuit. We replace the transistor by a symbol, and then this circuit has been first turned 90 degrees. So anti-clockwise you turn it 90 degrees, that is how you come here, replace this particular power supply by pair of resistors. Okay, so you are deriving the emitter based power supply from the collector power supply using a voltage divider. Okay, so the voltage across the emitter based junction in this particular circuit is given by R2 into VCC by R1 plus R2. So that is the voltage here. The small signal is superimposed through a capacitor connected here, which isolates this point from this point, so for DC conditions. Similarly, the output is taken from this point through a capacitor, so that whatever you connect here, for example if you connect a load resistor here, then this resistor will not affect the DC condition of this particular circuit. Now what we said is that this method of biasing the transistor and getting DC quiescent conditions is not very good, because you are trying to maintain the emitter base voltage constant. If the temperature of the transistor changes, which is going to happen very much during operation, because the transistor is going to dissipate power or because the ambient conditions are going to change throughout the day. So because of these reasons, for a constant emitter base voltage the current will change drastically as a function of temperature. So emitter current and collector current, these currents will change, and your quiescent point, output point will change, and that will affect your swing capability of the amplifier. Now how do we rectify this problem? So to rectify this problem, what we must do is that we must maintain the emitter current or the collector current constant instead of maintaining the emitter base voltage constant. Okay, then the emitter base voltage can be allowed to change. The change in emitter base voltage with temperature for a constant emitter current will not be much. This can be easily seen from the characteristics. So if you take a diode, these are the current voltage characteristics of any diode. Now for a higher temperature your current will be higher. So this is your curve for a higher temperature. Now what you find is that if you keep the temperature constant, if you keep the current constant, there is a small change in voltage. Okay, there is not much of a change in voltage. On the other hand, if you try to maintain the voltage constant, then you find that there is a large change in current, okay, with temperature. So this is for T1 and this is for T2. T2 is greater than T1. So therefore the idea is to maintain the current constant instead of the voltage being maintained constant. So how can we do that? That can be done easily as follows. You include a resistance here in series, so called emitter resistance, and you adjust your R2 so that you have a higher voltage here, so that the current in the emitter now is given by this voltage minus this voltage, this voltage minus the emitter base voltage, which is close to 0.65, divided by Re. Okay, so now your emitter base voltage will be close to 0.65. It may change a little bit because of temperature, but the change will be very small compared to the voltage that is coming here. So if you maintain, for example, 5 volts here, if this voltage is chosen to be 5 volts, then this is 0.65, it may change say around 0.6, 0.7, even if it changes that much, it is not much of a change compared to 5 volts. Change of about 0.1 volt in 5 volts is not much, and therefore the current through this resistance will remain almost constant with temperature. That is why this biasing arrangement is used. It is not in the scope of this particular course to discuss the biasing and circuit aspects of the transistor operation so much. This is done in the circuits course, but still we want to maintain a link between the device physics and the circuits, a discussion of these two. Now to complete this discussion, in order to get a good gain, this series resistance must be bypassed, so that for AC purposes you do not have this resistance and your gain is still given by the transconductance Gm of the transistor multiplied by load resistance RL in the absence of this resistance. If this resistance is also present, then parallel combination of these two resistances multiplied by Gm would be the gain. So with this we complete a discussion of the circuit configuration in which a transistor can be used as a common emitter amplifier. Now since we have now introduced the common emitter configuration as the most often used configuration, let us see the DC current voltage characteristics in detail in this particular mode of operation of the transistor. So common emitter output characteristics, we have already shown these characteristics. This is the circuit and these are the characteristics. So now we want to qualitatively explain how these characteristics are obtained. So what is happening here is that if you carefully note, we keep the base current constant and then we change the collector to emitter voltage. As a result, the collector current changes. So supposing you concentrate on any one of these curves, let us say the curve corresponding to 36 microampere base current. So you follow this particular curve. What is happening is you are keeping 36 microampere base current and then you are changing your VCE magnitude, and as a result the collector current is changing. So if you change your base current, you get a different IC VCE curve, and that is how you get this entire family of curves. So this is a circuit, you are maintaining the base current constant and you are sweeping the collector to emitter voltage and measuring the collector current. So this is what is important to note. Now what we will do is that we will take up any one curve for constant base current and explain how this kind of a shape of the characteristics arise, and then we will do it for a different base current, and that is how the entire family of characteristics can be generated. Now one point to note here is that the collector to emitter voltage is negative because we are considering a PNP transistor. So this means that collector is negative with respect to emitter. Similarly, the base current also is negative because it is coming out of the base lead, okay, and collector current is also negative because it is going out of the collector lead. But in our qualitative discussion, we will assume only the magnitudes of these quantities, okay, so that we do not have to constantly deal with negative quantities. So let us draw one curve that we want to explain. So for one base current, so instead of VCE, I am going to draw VEC here so that I get positive voltages, and similarly here I am going to draw modulus of IC, okay, so that I get positive quantity on this axis also. Now any particular base current, the curve looks something like this. This is what we need to explain. Of course, and after some time it breaks down. How do we get this kind of a curve? So let us start as follows. We draw the transistor, and now you are maintaining the base current constant. So this is the base current, this is IB. The first step would be to start from VEC equal to 0. This is VEC equal to 0. So VEC equal to 0, that is a point number 1. The emitter to collector is shorted. So this is the condition VEC equal to 0. What happens in this case is what we need to find out. Now our approach would be that we will draw the minority carrier distributions in the emitter, base and collector for different voltage conditions, and from the minority carrier distributions we will get the information about the collector current. So here if you draw the minority carrier distribution for this condition, it would be something like this. Now please note that we must try to draw all diagrams to scale. Now this base width is about a micron. I am not saying exactly 1 micron because you know that your depletion widths from either side of this in this region, that is from the emitter and from the collector, they will slightly reduce the base width. We are now discussing a qualitative, discussing at a qualitative level. So we are not interested in exact magnitudes. So this is about a micron, and the diffusion length in the emitter, as we have noted, is 33 microns. So strictly speaking, the distribution of the minority carriers, excess minority carriers, would be fairly over a fairly long distance here as compared to the base width. So let us draw it something like this. This is excess minority carrier concentration in the emitter. We are going to assume long emitters, okay. As we have said in the beginning, we assume an ideal transistor. In ideal transistor, the doping levels in the base, emitter and collector are uniform, and the emitter and collector regions are fairly long. Now what about the excess carrier concentration in the base? According to this, whatever is the emitter base voltage, the collector base voltage is also equal to the emitter base voltage. Because this is shorted, obviously this voltage should be equal to this voltage, okay, in magnitude. They will cancel each other, and that is how you get a 0 voltage between emitter and collector. So this means that from the diode theory, the boundary values of the excess carrier concentration would be same at this end as well as at this end. So this is your excess carrier concentration in the base. Now please note that this value would be 10 times this value, okay, because doping in the emitter is 10 times the doping in the base. So this is again not to scale. If I have to show it to scale, I must raise it up further. So at least approximately to scale. So 10 times this, let us assume this is approximately 10 times, not exactly 10 times but approximately. So something like this. Now what happens in the collector? The collector excess carrier concentration would be 10 times this value, okay, because collector region doping is 10 times less than the base region doping. Now this really cannot be shown here. So this means that the way we have started the diagram is not exactly correct. The correct approach is always to look at the maximum value and first draw that value and then draw the other parameters which have smaller value. That is the way you must draw whenever you want to draw the diagram to scale. So having understood that the maximum concentration will occur in the collector at the depletion edge here of the collector junction, what we should do is let us restart as follows. So we first draw this excess carrier concentration because this is also forward bias now under this condition. Please note that this is a forward bias across the collector base junction. Now this is 1/10 of this inside here. So still I cannot show 1/10, but at least roughly very small, and this here is something like this, okay, because this is again 1/10 of that. So this is how the excess carrier distribution would be. This is excess electrons in P region, this is excess holes in N region, this is excess electrons again in the P type collector region. Now from here what do we gather about the collector current? So let us draw the flow diagram to show the various currents here. So what is happening is that this is P, this is N, this is P. So electrons are being injected into the collector. So this we will show as, we will show a dotted line for electrons, and all these are recombining. Now similarly this shows that holes are being injected into the base from the collector. So or rather what we will do, we will reverse this. Let us show the electrons below and the holes above. So the electrons being injected will be shown like this, and the holes injected from here is shown in this way. So holes are injected into the base from the collector and also from the emitter, because both these are forward biased, and you can see that the slopes here are like this. So these are holes injected. Now what happens to this hole current? Obviously it recombines here. Similarly the N region injects electrons into the base injects electrons into the emitter, so you have electrons injected here. Now with what will these holes recombine? They will recombine with electrons, so you have to provide electrons there for recombination in the base. So all these electrons, that is electrons which are injected into the collector, electrons which are injected into the emitter, and electrons which are recombining with the holes in the base, are provided by the base contact. So here these electrons will recombine with holes. So this is your so called emitter current, and here these electrons will recombine with holes here. So this is your so called collector current. Please note that the arrows indicate the direction of flow of the particular carrier, and dotted line is electrons. So if electrons are flowing in this direction, the conventional current because of electrons would be in opposite direction. This is to be understood. So the base current is outward, okay, conventional current is outward, electron current is inward. Now to simplify the picture, we will use the fact that in modern transistor the recombination in the base is negligible because base is really very thin. Alpha is therefore decided by the injection efficiency, or which is equivalent to saying that alpha is decided by the current that is injected from the base into the emitter. So alpha is decided by this current and not recombination here. Therefore what we will do is this part of the picture can be removed to gain a simple understanding of the situation. So we will remove this is negligible. So this is negligible means this also can be neglected, so we remove this. So now this is the picture really, this is approximate picture. So clearly there is a collector current which is present here, and also the base current is equal to the electrons injected here plus the electron injected here. Now from this diagram you can very clearly see that the excess carrier concentration in the collector is much more than the excess carrier concentration in the emitter because of the difference in the doping levels, and because the forward bias across this junction is the same as forward bias across this junction here, emitter junction. So therefore this current will be much more than this current, okay, because the amount recombining here would be much more than the amount recombining here. Therefore we could even remove this picture and we are left with just this picture. Now this is very easy to understand. This means that according to this there is a collector current which is equal to the base current. So IB, whatever IB is flowing here, in fact most of this IB is flowing into the collector, and what is interesting is that the collector current is flowing in, okay. So we have seen, if you look at the characteristics on the slide, the collector current is shown to be negative and it is flowing out. So obviously what this means is that in this case the current should be shown on the opposite side to the current shown on the slide. So let us understand this very clearly. This means that when we draw this curve, actually it is not correct to say when VEC is 0 the collector current is 0. Actually the collector current is inward into the PNP transistor and therefore it is positive, or in our nomenclature, since we are showing negative currents in this direction, the current that we want to show for V is equal to 0 should be shown in the negative axis, because negative currents are shown along this particular axis, the positive current should be shown along this axis. So we will now redraw this curve to start with. Now our curve is as follows. For V is equal to 0, you have a current which is equal to the base current like this, okay. So this is the IC corresponding to V is equal to 0, equal in magnitude to IB. So that completes the analysis for the condition V is equal to 0. For V is equal to 0, IC is equal in magnitude to IB, approximately equal in magnitude to IB. Now we can use a similar approach and now proceed to derive the remaining part of the curve. Now, it is very clear from here that the next curve point that you would like to analyze would be, you expect the curve to rise up like this. So the next point you would like to analyze would be the point corresponding to IC equal to 0, okay, IC equal to 0. What is the value of VEC? That is this value VEC for IC equal to 0. Now please note that I have removed the modulus of IC here, and I am just showing IC. It is understood that we are going to plot the current that is into the transistor on this side and current out of the transistor on this side. So let us now analyze similarly the condition IC equal to 0. Now when will IC be equal to 0? Notice that you are moving towards, in terms of this, you are moving towards more and more positive VEC as you go in this direction. This means now that you are going to include a power supply here in this direction, a small value, and then you are going to increase this power supply slowly until you end up getting IC equal to 0. So let us draw. So now this condition, now we want to talk about is IC equal to 0. So we start from scratch and we remove this distribution that we had earlier in this diagram. And then we remove this. Now what happens? This is forward biased. This has to remain forward biased, although its value of the forward bias may change, because it has to remain forward biased because the current is outward here. So there has to be a current in this direction. So when you apply a voltage in this direction, what is going to happen is that this forward bias will start reducing. Okay? So now your condition is VCB is less than VEB. As you start increasing your VEC, this is VEC. So when you want to draw the excess carrier concentration for that condition, it will be as follows. So you see that the collector base voltage forward bias is less than emitter base forward bias. That is why this concentration here is less than this concentration here, excess carrier concentration here. Okay, this is again we are using the law of the junction. So now we need to find out when, for what kind of a voltage condition will the current on the collector become 0, and how can the current become 0? So let us draw the flow diagram again as we had done earlier. Now when we draw the flow diagram, we will continue to ignore the recombination in the base, because we are assuming a modern transistor. We have said that in a modern transistor the recombination in the base is negligible, and that helps us to simplify the picture greatly. So again you have holes being injected from emitter to base. Part of this is recombining here and the remaining is injected into the collector. So this slope here shows that holes are being injected into the collector. Now this slope here shows that electrons are also being injected into the collector from the base. So this is shown like this, electrons being injected from base to collector. You have electrons being injected from base to emitter as we had earlier. So you have this also, and we said that we will neglect the recombination, so we will not show this arrow. Now to complete the picture, these electrons can recombine, have to recombine with holes, so you have this, and these electrons have to recombine with holes, so you have this. So this is your emitter current, and now what you find here is very interesting. You have electrons being injected from base to collector. You also have holes being injected from base to collector. These holes are coming because they are injected from emitter to base, and recombination in the base is very small, so most of them are coming into the collector. So you have holes and electrons moving in the same direction across this collector junction. That is a very interesting situation. If you have holes and electrons both moving in the same direction, then their current will cancel out if the magnitudes of the holes and electron currents individually are identical. That is the interesting situation here, because of which the collector current is 0. Though you have flow of both holes and electrons, since this flow is in the same direction for both carriers, you can see here that the holes here are recombining with electrons. So there is no current here, right, that we were showing earlier. This is how you get 0 collector current. So in fact one can analyze this situation, write down equations and impose this condition that this whole current should be equal to this electron current, and one can determine what is the value of the collector base voltage and what is the value of the emitter base voltage, and therefore what is the value of VEC for which this condition would occur. So that completes the discussion about this condition, that is IC equal to 0. So evidently now the next step is to move ahead like this on this curve. Now what do you expect? What is the next point? We can see from here, this diagram, that as you go on increasing your VEC, the forward bias here will start decreasing. The forward bias here was maximum when VEC was 0, and when we start increasing VEC, the forward bias start reducing. So obviously a stage will come when this forward bias will become 0. So the next step is to analyze the condition when VCB is equal to 0. Which is same as saying VCE is equal to VEC is equal to VEB. So this is the next condition that we want to analyze. So again now we will rub this excess carrier concentrations and we will redraw them for the condition that we now have. Now it is very easy to draw the excess carrier concentration for this condition, because we have actually analyzed the transistor in the beginning for this condition, collector base voltage equal to 0. So 0 collector base voltage means the excess carrier concentration is 0 here. So you have this excess carrier distribution in the base, then you have this for your emitter, and you don't have any excess carrier concentration in the collector because the collector base voltage is 0. So in this case we have already drawn the flow diagram. You have holes being injected from emitter to base, a small part of them recombine and then remaining get injected into the base, into the collector. You have current, electron current injected from base to emitter, and this electron current recombine with holes. These holes which are recombining here need electrons for recombination. So this is the electron current, and this electron current is supplied by the base. Again we neglect this recombination in the base, so we remove this. So this is in fact a very simple flow diagram. Okay, so IC. Now what is the value of IC in this condition? We know that IC is equal to beta times IB. If you want to write IC in terms of IB, IC is beta times IB. So you go up like this, and so this is the condition corresponding to VCB equal to 0 and IC is beta times IB. So this point is beta times IB. Again we are not taking into account the fact that the current is outward and it should be negative, we always assume here for the purpose of analysis on this board that the currents that we are talking of are always the magnitudes of the currents. So IB is the magnitude of the base current. So beta times IB is the collector current here. Now if this is IB and if this is beta times IB here, then this diagram is not to scale, because we have seen that the transistor beta is about 100, okay, that for the example that we considered. So it can be 50 or it could be even more than 100, okay, it varies, but still it is a very large value. So if you want to draw the diagram to scale, really speaking, this current should be shown, this point should be shown very close to origin on the scale, and similarly this voltage is also very small because it is a difference of two forward bias voltages. Okay, if you recall, the VEC is the difference in forward bias across emitter base junction and collector base junction. So this voltage also is very small, it turns out it is about tens of millivolts. So IB is in microamps or tens of microamps, and this voltage is about tens of millivolts, whereas the collector current on this axis is of the order of milliamps, and this voltage is of the order of volts or tens of volts. So therefore on such axis what happens is that this point and this point appear very close to origin, okay, tens of millivolts on a 10 volt axis and microamps or tens of microamps on a milliampere axis, okay. So this is very close, and that is the reason why this point appears to start from origin. Let us look at the current voltage characteristics on the slide. You see that this current appears to start from origin. Now we understand from detailed analysis that it is actually current is not 0, IC is not 0 when VC is 0, okay. IC, there is a small current, but because that current is very small, okay, you really do not see, okay, that small amount of current. So therefore these characteristics are shown to start from origin, okay. Now let us proceed further. What will happen as you increase your VEC further? So we need to move beyond this. Now we are increasing the VEC further. What is going to happen is that now your base width modulation is going to come into picture, okay. This we have discussed in our earlier lecture, that what is the effect of having a reverse bias across the collector base junction, and we said there are two effects. One is there is a reverse leakage current ICO, and another is that there is base width modulation, okay, and this base width modulation has an effect on amplification. Now right now we are interested in the base width modulation effect on the IC VEC characteristics. So for that purpose we must now show the base width also clearly. So now let us redraw this diagram. So now you have VCB less than 0, collector is negative with respect to base. Now in this case so now we are showing the depletion region of the collector junction, which we had not shown so far. Now the excess carrier concentration on the collector side. So this is the depletion region. Again, this is not exactly to scale, but at least roughly to scale, in the sense that depletion region on the collector side of the junction is more than the depletion region on the base side of the junction, okay. Now here once you reverse bias the collector base junction, and if the reverse bias is more than 3 times Vt, then we know that excess carrier concentration here would be equal to the negative of the minority carrier concentration. So it would be something like this. This is what is responsible for the current ICO. Now if you draw this diagram to scale, then minority carrier concentration is very small compared to the concentration when there is a forward bias present, because when there is a forward bias, you know that minority carrier concentration is multiplied by exponential of the forward bias by Vt. So when you draw it to scale, in fact you will not be able to show this at all. Okay? So therefore the concentrations of minority carriers in the collector is cannot be shown if you draw the diagram to scale. Now let us write the equation for collector current in this region. Okay, this is the so called active region. So this corresponds to VCB equal to 0. Beyond this you have the active region of the transistor, and it is in this region that we have analyzed our transistor so far, okay, to explain the transistor action and the amplification and so on. It is this region that is very useful, because here in this region most of the emitter current is transferred to the collector. So what is the equation for IC? Now we know that IC is equal to alpha times IE when collector base voltage is 0, and when collector base voltage is negative in a PNP transistor, that is it is reverse biased, you have this. This is a basic equation for the transistor. Now here we want to express in terms of the base current, because it is the base current that is being maintained constant. So to do that, what we will do is this transform this equation so that we write IE, replace IE by IC plus IB. IE is equal to IC plus IB. So if you do that and you rearrange this equation, you will get IC into 1 minus alpha is equal to alpha times IB plus ICO. Okay, so now this is the condition. For VCB less than 0, and it is a PNP transistor. So again rearranging this, you get IC is equal to alpha by 1 minus alpha into IB plus 1 by 1 minus alpha into IC naught. Now this quantity is nothing but beta, so your equation is IC is equal to beta times IB plus beta plus 1 times IC naught. Now this is what is important. When IC is controlled by IE, the current that comes about is IC naught in the collector because of the reverse saturation current of the collector base junction. But when you are controlling IB and IC is being controlled by IB, in that condition, in that configuration, you have beta plus 1 times ICO coming there. There is a multiplication of this ICO, okay, by beta. So this is the equation for IC. In this particular active region. Now look at this equation carefully. If we assume that the beta is constant with the emitter collector voltage, then IC should be constant because IB is being maintained constant and ICO also is constant. We assume temperature to remain constant. IC should be constant. Okay, so that means you will have a curve which is just like this, flat. But we find, if you look at the slides, look at the slide, that the current is increasing slowly, it is not constant. Now this is because of the base width modulation effect. So that is what we have to see here. So because of base width modulation, as your collector base voltage reverse bias increases, as you increase VEC, your base width starts shrinking. This is what you can see here. Okay, so for zero bias you had this particular excess carrier concentration, but for reverse bias you have this. and if your reverse bias increases you will get this. So this is VCB equal to 0, and progressively this is VCB becoming more negative. So you can see now the current will not be, collector current will not be constant, because you can see the slope is in fact increasing, and that is why the collector current will also increase. From excess carrier concentration it is very clear why the IC increases, because of base width modulation. Now we can actually estimate the extent of increase using this equation. That is another way of also looking at it. When your base width is less, your beta is more. So what is happening in this equation, beta is not constant with VCE. Okay, so the situation is that beta increases with as VEC increases. And this is because since base width WB falls. So because of that, because of the increase in beta with VEC, instead of a flat current you get a current that is increasing like this. So you have a slope. Let us try to get an idea of this slope, okay, because as we have done earlier, we have tried to get an idea of these magnitudes. How much is this voltage, how much is this current? We should have some idea so that we know how the curve looks like. Now how much will this voltage be? For VCB equal to 0, this voltage is nothing but VEB, right? This is the forward bias. So forward bias means about 0.6, 0.7 volts, and this is beta times IB, so this is of the order of milliamps. Now how much is the increase in current for a certain increase in voltage? Let us try to see that. Now for this purpose we must try to see how beta changes with VEC, or in other words how beta changes with WB. Okay, so let us try to write an equation for beta as a function of WB. This we can do easily because we have written an equation for alpha. Now alpha was 1 minus WB square by 2 LB square minus WB by LE into DE by DB into NB by NE. So it is very easy to remember these equations once you understand the physics behind them. Okay, so one must try to remember formulae by understanding the physics and not try to remember formulae as you remember phone numbers. Okay, when you understand the physics it is very easy to remember the formula. Now if this is alpha and beta is alpha by 1 minus alpha, so therefore we can approximate numerator as 1 to avoid a simple to avoid a complicated formula, and 1 minus alpha would be simply this plus this. Now further we have said that in modern transistors this term is very small compared to this term. Okay, so 1 minus alpha can be simply written as WB DE NB and LE DB NE. Okay, so for a modern transistor which is governed by, whose beta is governed by injection efficiency, this is the beta. Clearly from here we can see beta is proportional to 1 by WB. So as your WB changes your beta will increase, other things we will assume to remain constant. Now based on this we can try to find out how much increment in current will be there for a given increment in the emitter to collector voltage. We shall denote using a symbol beta naught the value of beta corresponding to VCB equal to 0. So beta is equal to beta naught when VCB is 0, and similarly the base width as WB naught for that same condition. Now we have beta by beta naught, where beta corresponds to any other value of VEC. So when VCB is equal to 0, you know that VEC is equal to VEB. For any beta is the value for any VEC. So beta by beta naught can be written as WB naught by WB. So WB is the base width for any voltage condition, okay, because beta is inversely proportional to WB. Now this WB we can write as WB naught minus the change in the depletion width in the base from the collector side. Let us call it as delta XB. Okay, what is delta XB? Delta XB is the change in the depletion layer on the base side at the collector junction. So therefore this is 1 by 1 minus delta XB by WB naught, okay, that is your beta by beta naught. Now let us see what is delta XB. So this is your collector junction, and at 0 bias, suppose this is your depletion width, this is the base, okay. Now any other bias, your depletion width will be this. So this is what we are calling as delta XB. Now this delta XB can be written as follows. We know what was, let us take a specific example, okay, the example that we considered, a quantitative example. For that example we had found that this depletion width was 0.085 microns. And the voltage corresponding to this, which was the built-in voltage, was, so this corresponds to psi naught in the collector junction of 0.637 volts. So please look into your notes and you will find this. Let us take a specific case. Supposing I want to find out the depletion width on this side for, let us say, 9 volts reverse bias, okay. So VCB is equal to minus 9 volt. What will be the depletion width? Now one can find this out very easily. You know that this depletion width, we will call this XB. So this is XB. So XB is proportional to square root of the potential drop across the depletion region. So we will write XB naught, which is the XB for VCB equal to 0. So following this same convention here, so we write XB is equal to XB naught. XB is the depletion region on the base side of the collector junction. XB naught now depends on psi naught E, psi naught C, collector potential, built-in potential across the collector junction. So XB by XB naught we can write is equal to square root of psi naught and the collector junction plus the value of VCB by psi naught of the collector junction. So delta XB therefore can be written as XB minus XB naught, which is equal to XB naught into XB by XB naught minus 1, which is equal to XB naught into square root of psi naught C plus So this also can be simplified 1 plus VCB by psi naught C minus 1. Okay, this is the value of delta XB. Now substituting the typical numbers from our example, delta XB for we are estimating for VCB equal to minus 9 volts. Delta XB is equal to XB naught is 0.085 microns into square root of 1 plus this is 9 by 0.637 minus 1. This 0.085, so this whole thing is micrometer. So that is your delta XB. Now you can use your calculators and try to estimate this value, okay, which corresponds to VCB equal to 9 volts negative, okay, that we should write here. So delta XB for VCB is minus 9 volts. This is the value. You can use your calculators and estimate, but we will do a very rough estimation. We must be able to do these kind of approximations, okay, and not always think that we must have a calculator with us. So 9 by 0.64, okay. So let us say this will be 9 by 0.6. So this close to 15, okay. So this quantity will be between 15 and 16, 1 plus this. So now square root of 16 we know is about 4. So 4 minus 1 is about 3. So this is approximately equal to 3 times 0.085 micrometer, okay. That is your delta XB. Now we can substitute that here, and we recall that WB naught was about 0.8 microns, okay, for us. When collector base voltage was 0, the base width was about 0.8 microns. So we can therefore write beta for VCB equal to minus 9 volt by beta naught is equal to 1 by 1 minus 3 into 0.085 by 0.8. Approximately, this is approximately equal to, okay. So this is about 1/10, so this is about 3 by 10, so this is about 1 by 0.7, okay. So which means the beta is 1 by 0.7, so about 1.4 times beta naught is what you get. So which means what you find is beta is increasing by 40%, okay. So this means that you will have a lot of change in the collector current when you go from this point, which is VCB equal to 0, to the point VCB equal to 9, okay. So you will have a current increasing from this value to 1.4 times this value, okay. So this gives you an idea of how much change in the collector current is there for change in collector to emitter voltage. We will continue with this discussion in the next class.